This is part 8 of the Module 11 lecture. In this part, we will talk about linear correlation, and this corresponds to section 13.4 in your textbook. All right, in terms of what we call a linear correlation analysis, the objective is to determine if there is a linear relationship between two continuous random variables, x and y. And the way to assess this linear relationship is 1, graphically using the scatter plot, and 2, by testing the by calculating the correlation coefficient and testing it to see if it is statistically different from 0. All right, the correlation coefficient is very important. It measures two characteristics: the strength and the direction of the linear relationship between two variables. All right, the correlation coefficient, the population correlation coefficient, we use the letter rho to denote that population correlation coefficient. So this is the letter rho. And the sample correlation coefficient, we use the lowercase r to designate the sample correlation coefficient. Now, both of these coefficients have values all the way from -1 all the way to 1. So they can take any value between -1 and +1. And that's what I'm showing here at the bottom. All right, how we calculate this correlation coefficients? Well, for the population correlation coefficient, we rely on the actual population mean of the x values and the population mean of the y values, and we calculate it this way. Now, for the sample correlation coefficient, we don't have all the data for the population, so we don't know the population means for the x values and the y values, so we use the sample mean for the x values and the sample mean for the y values, the same in the denominator. Now, you could calculate the sample correlation coefficient using these sums, or you can calculate using the sum squares of xy, the xx, and yy. You will have these sum squares from your calculations of the correlation of the regression intercept and slope coefficient, and from calculating the standard deviation of the residuals. Now, one thing to note, I don't like to make too much of this, but the r squared, the coefficient of determination, is equal to the square of the correlation coefficient, but only for simple regression analysis. This equality breaks down as soon as you have more than one x in the model. So again, not something that critical, but you may see it in your book. All right, but the main thing is to recognize that this is a equation that we will use to calculate the correlation coefficient. All right, the correlation coefficient, the way to interpret it is that the closer the correlation coefficient, either rho or r, is to +1, then the stronger the linear relationship between x and y. Now, I use these ellipses, these red ellipses, to give you an idea of how close the points are aligned onto a straight line. The narrower that ellipsis is, the skinnier it is, the higher the correlation coefficient. So for example, in this particular case, this is a correlation coefficient of 0.89. And we call it a positive linear relationship because as x increases, y increases. Now, if the correlation coefficient, the value of it, is getting closer to -1, that implies that we have a strong negative relationship. And you can see the only difference between these two figures is not that the ellipsis is narrow on one hand, but also now is pointing in the opposite direction. So instead of going like this, now it's going like that. This implies that we have a negative linear relationship. And it's called negative or an inverse relationship because as x increases, y decreases. And that will be seen with the negative value in the correlation coefficient. So remember, the closer these correlation coefficients get to 1, the stronger the relationship. If it is closer to +1, so the stronger the positive relationship. If it is get closer to -1, then the stronger the negative relationship between the two variables. On the other hand, if the closer these correlation coefficients are to 0, the weaker the relationship between x and y. Another way to see it is if you could see these ellipses around the points, you see that these ellipses are wider, and they get as wide as a circle, like in the right-hand case. And so as the ellipses start getting closer and closer to a circle, then the lower and lower the correlation coefficient is. So here is a correlation coefficient of 0.42, and there's a correlation of practically 0. But you can see the arrangement of points. All right, another thing to keep in mind is that you may have nonlinear relationships. And even though you have a nonlinear relationship, the correlation coefficient may take a large value, like on the left side. So in here, even though you have a curvature, the straight line will still have indicate that there is a strong relationship between x and y. Or you can have this situation where the line is very close to the horizontal line, so the correlation coefficient is almost 0, but really the behavior is not linear. This is more of a parabola or a square relationship. So keep in mind on that, and that's why the scatter plots are very useful to see if the relationship is really linear or nonlinear. All right, so now once we calculate the correlation coefficient, one thing that we'd like to know is if that correlation coefficient, in other words, using the sample correlation coefficient, we want to determine if the correlation coefficient of the population is 0 or not. Because if it is 0, means that x and y are not related. So the hypothesis, the null hypothesis that we will use in this test is that the correlation coefficient is 0. Or you can have different alternative hypotheses. You may be interested in simply demonstrating that there is a significant correlation. You don't care if it is negative or positive. In that case, we'll have the two-tailed test because we just want to show that the correlation coefficient is non-zero. If you're interested in determining if if you have a significant negative correlation, then you have a left-tailed test because you're trying to show if rho is less than 0. If the interest is in determining if the correlation is positive, then you will have a right-tailed test because then the correlation coefficient will be larger than 0. So in here, you could have the three alternatives, and it depends on what alternative hypothesis you decide that you want to test. All right, the procedure is the same that we've been using all along since Module 8. And so the first step is determine the null and the alternative hypothesis, which is what we have done here. And then in the next step is determining what distribution to use and what test statistic to use. In here, the test statistic for performing a hypothesis test with the correlation coefficient is defined as this. So where the R observed is the correlation coefficient that you calculate from the data. And so there are two things that you require for this calculation. So the value of the sample correlation coefficient and the number of observations in the data set. All right, so assuming that these two variables are normally distributed, then you will use the t-distribution with degrees of freedom of n-2. Again, in here we don't see the sample correlation, the standard deviation of the sampling distribution of the correlation, but in here we are estimating it with the denominator of this quantity. So that's why we're using the t-distribution. But the main thing here is to justify the use of the t-distribution by recognizing that the two distributions, the two population distribution of the y's and the x are normal. So remember, this is the condition to justify the use of the t-distribution. All right, so if you decide to use a critical value approach to test a null hypothesis, well, you will determine the rejection regions, or find the critical values to define the rejection regions from table 5. using alpha or alpha over 2, depending on which test you have, and the degrees of freedom of n minus 2. And the same rule applies. If the T observed is in the rejection region, the null hypothesis is rejected. And here I'm showing you the rejection regions for all 3 cases. And this is the same diagram that we had in module 10 and in module 9. All right, if you decide to use the p-value approach, again, the same rule as before. If the p-value is less than alpha, we reject the null hypothesis. If the p-value is larger than alpha, we do not reject the null hypothesis. And how we calculate the p-value, well, depends on what is the direction of the test. So if you have a left tail test, you use the probability that t is less than the t observed. If you have a right tail test, you use the probability to the right of the t observed. And if you have a two-tail test, we multiply 2 times the probability to the right of the observed t-value. If you like to use Excel, here are the formulas for each of the situations. All right, so, and one other thing that is important to realize when it comes to interpret the decision about the null hypothesis, that you need to note that by rejecting the null hypothesis does not necessarily mean that you have a strong relationship between y and x. Maybe you have a lot of data, and that will distinguish a small correlation coefficient, but that correlation coefficient may mean nothing in terms of the relationship between x and y, but still the null hypothesis will say that that's significantly different from 0. Or also you may find that you have or do not, you have a strong relationship, but it's not linear. So it's very important that when you interpret the null hypothesis about the population correlation coefficient, you supplement that with the scatter plot and the magnitude of the sample correlation coefficient. This is very important, and I'll show you in the coming example how we use these two to help in the interpretation of the null hypothesis. All right, so I will stop here, and the next recording we'll work on this example.